Good day! Welcome to CALCUFORNIA, the city full of problems, but with answers. Let me take you to the Deriva Village, specifically Rate Street. This street is known for having problems involving related rates. Let me give you a tour. Let's go to the information center first.
Problems involving related rates ask about the rate at which one quantity is changing, mostly in units of distance over time, area over time, or volume over time. These problems answer the questions how fast, how quickly, and at which rate. These problems are also real-life applications of derivatives, specifically implicit differentiation.
Are you interested? Well, let's move to the preparation center to know the different steps in solving these kinds of problems.
With solving problems involving related rates, there are 4 simple steps we have to remember. The first step is to draw a picture of the physical problem. When you try to visualize the problem, you can notice that the problem involves shapes and figures that you might be familiar with. The second step is to write an equation that relates the quantities of interest. In this step, you can use almost every equation or formula you know. Just keep in mind that you have to relate the different variables in a problem together. This equation can be geometric, trigonometric, or theorems, like the Pythagorean theorem. Step 3 is very important. In this step, we will take the derivative of the equation with respect to time. It's important to follow the chain rule here. The last step is the easiest of all, and that is to solve by substituting the values. Again, here are the steps in solving problems involving related rates. Hope you have fun!
Are you ready? We're now going to the activity center to have some fun. Here we have the 3 problems. We're gonna go through them one by one. Let's go!
Here we have our first problem. The radius of a particular circle increases 2 millimeters per second. As a result, its area changes. How fast it is area changing when its radius is 30 millimeters. This is an example of an expanding circle problem. As our first step, we draw the problem, which is a circle. Write the given, that is the rate of the radius as it is increasing with respect to time. This is denoted by dr over dt, and its value is 2 millimeters per second. What we are asked to find is dA over dt, which is the rate of the area changing with respect to time, when the radius of the circle is 30 millimeters. Now, we must relate the 2 variables a and r together to find an equation to use. One equation we can use is the formula in finding the area of a circle. The area of a circle is equals to pi r squared. As you can see, this formula has 2 variables a and r, which are in the problem. However, we should not substitute yet, since that we are talking about rates.
Before substituting, we will differentiate the equation with respect to time. We must follow the implicit differentiation and the chain rule in this step. We do this by multiplying the equation by d over dt on both sides. By doing so, our new formula will be dA over dt equal to pi 2r times dr over dt. Keep in mind that we are looking for the rate of the area changing with respect to time, which is dA over dt. Now, we can substitute the values given. Pi stays as well as 2. We change r to 30 millimeters, dr over dt to 2 millimeters per second. Simplify the equation, and in the end you should get 120 pi square millimeters per second or 376.991 square millimeters per second.
Are you getting familiar with it? Let's go to the second example.
Our next problem is an example of a conical tank problem. An inverted cone is 40 centimeters tall, has an opening radius of 16 centimeters, and was initially full of water. It is now being drained of water at a constant rate of 30 cubic centimeters per second. The water surface level falls as a result. At what rate is the water falling when the water is halfway down the cone? By drawing the problem, we can visualize the situation as well as put the given values accordingly. The height of the cone is 40 centimeters and it has an opening radius of 16 centimeters. We are also given the rate of the draining water in the cone with respect to time, which is negative 30 cubic centimeters per second. This is written as dV or dt. Notice how we made it negative. It is because it is decreasing. We have to look for is the rate of the water falling when it is halfway down the cone. This can be referred to as dH over dt. Now, we must relate the variables v and h together and come up with a formula that has these variables. One formula is the formula for finding the volume of a cone. This is equal to 1/3 pi r squared h. We will use this equation for the problem. Now, notice that there is another variable which is r. As you can see, this variable is not given. We have to replace r so that we can go into solving. How do we do that? Notice that there are two triangles in the problem, the cone and the water as a figure inside the cone. They are considered as similar triangles. Now, the ratio of the base of the small triangle to that of the big triangle must equal to the ratio of the height of the small triangle to that of the big triangle. When we write it, we have this equation right here. We can cross-multiply this problem, and we eventually get to replace r with h. Now that we have replaced it, we can now go on to our main problem.
The new equation is 1/3 pi quantity 2h over 5 squared h. We can actually simplify this further to have an easier equation to follow, and this is 4 over 25 pi h cubed. Again, we must not substitute values yet. Instead, we can differentiate the equation with respect to time. Multiply the equation to d over dt on both sides, and eventually we will get the dv over dt equal to 4 over 25 pi h squared dh over dt. We can now move to substituting the values. dv over dt becomes negative 30 and h becomes 20. Let's simplify 20 squared and we will get 400. Now we can actually multiply 404 from the numerator of the fraction, and we will get much simplified equation, 1600 pi over 25. Keeping in mind that we are looking for dh over dt, our next step is to move this fraction to the other side by reciprocating it. Now, we are closer to finding the value of dh over dt. Multiply negative 30 to 25 and simplify the fraction. In the end, we get negative 15 over 32 pi or negative 0.1492, remainder to put in the unit, which is centimeters per seconds.
Come on, we only have one problem left. Let's do this.
For the last problem, two cars are approaching the same intersection. What is the rate between the two cars? We illustrate the situation of two cars and substitute the given into the drawing. The first car is approaching at the speed of 40 miles per hour, and right at that moment, the distance between the car and the intersection is 0.6 miles. The second car is approaching at the speed of 60 miles per hour, and the distance between the car and the intersection is 0.8 miles. The goal is to solve for the rate, which is the distance between the first car and the second car.
By using the Pythagorean theorem, we can find the rate. The first step is to find the derivative of the Pythagorean theorem and substitute the given. If you are confused about why the rate of the cars is negative, it's because they're decreasing by their given miles per hour as they approach the intersection. As you can see, the S is missing, and to find that, you should substitute the given in the original Pythagorean theorem and simplify. The answer for the S is equal to 1, and now, we can substitute the given and calculate. The answer will be negative 72 miles per hour. The rate between the two cars is decreasing as well as the given rates for each car.
Wasn't that fun? Well, I'm gonna head over now, go to the museum and meet some cool people.